So, hello everybody, it's me Long again, and I'm very happy because I can see you. Well, I hope that you just had a good time with your families, your parents, your children, your grandmother, etc. And anyway, we have one common goal right here today that need to be accomplished. Lecture 1, Basic Principles of City, Part 2. Well, I hope you're ready, but if you're not, just be calm because as always, I promise I'll be by your side all the way down. Okay, let's go. Well, we're going to the computer tomography definition section. Well, just like I say in the previous video, our CT machine has a narrow X-ray beam, and this beam goes through the patient body. And after interacting with our body, the remaining X-ray beam meets the detector, radiation detector, and the detector scan our beam profile and translate them into data. And our computer in the CT system will in charge of processing our data, and ultimately we have cross-sectional images. Yeah, that's the workflow of CT, the protocol of how CT work. So we have a photo right here that demonstrate the analogy of the way CT works. It's called the bread analogy. Maybe one of the most analogy in all CT lecture. Yeah, you can see this right now that bread is cutting into slices, just like the way our CT system divides our brain into sections, into slices for easier watching. And the crust of the bread is comparable to the patient's skin. Besides, the white portion inside the bread is comparable to the internal organs of the patient. Moreover, I have two notes for you right here. The first one is the slide thickness is defined by the z-axis. Well, there's a photo that demonstrated quite good about the idea that I'm talking about to you. So from now on, whenever I say about slide thickness, please just remember the slide thickness is defined by the z-axis. This is the z-axis. And the second line I wrote here is mean by just for the circumstances you wonder what is the object that control the slide thickness. Well, let me have some simple explanation for you. The slide thickness is controlled by the beam width, and the beam width is controlled by the collimators. As you can see right here, the collimator limits the X-ray beam width. So the collimator also have the ability to modify the slide thickness. Well, there is two kinds of collimator. The first one is the pre-patient collimator, which is set just behind the X-ray source but above our patient. And the second kind of collimator is the post-patient collimator, which is set behind inferior of our patient, but just above the detector. Well, about the collimators and the slide thickness. The second large knowledge I note here is about the way we differentiate CT data and CT image matrix. Well, CT data is sectioned into three-dimensional elements, and the CT image is formed by the two-dimensional matrix. For example, if you're just wondering why there's a difference in the data and the image, the reason why CT data is sectioned into three-dimensional image three-dimensional elements called voxel because, as you remember, our X-ray tube rotates around our body, and scan outer body in every view. So the data from the beam profile, it contains every single data, every single information of outer body in every view, in every angle. So that's reason why it is sectioned into three-dimensional elements, because we are human, and human are the object, the 3D object. Yeah, we are the 3D object, but the image, I mean the conventional image, is just a 2D object. So the reason why the city image is formed by the two-dimensional matrix, by rows and columns, and each one of them, every single rectangular or square in this matrix called pixel. Just remember that, my friend. Voxel 3D, pixel 2D. Wow, so far so good. Now let's get into another section. It's about beam attenuation. Oh, it's really cool. It's a cool part because this is beam attenuation. It's one of the most important definition that you have to remember, because this is the cause of every single process in the CT system. Let me explain to you. The beam attenuation is the level of the beam intensity is reduced by going through the object. Just like the blue line right here, you can see that the degree to which an X-ray beam is reduced by an object. You can imagine that our body, a patient, is the barrier, and the X-ray, when it meets the barrier, it loses its energy, it loses its intensity, it loses so many things, and this reduction in the intensity of X-ray beam is called beam attenuation. And that reduction process phenomena depends on the thickness, the density, and the atomic number of the material. Here, what it means? It means with the bone, with our lung, with our kidney, there is a different beam attenuation phenomena that occur differently, just like that. And that is the reason why we can use this phenomena to create the images that can distinguish our organs on that image. Why? Because every single organs, every single tissues, every single structure have the different beam attenuation phenomena when X-ray meet it. So in another way, they have a particular linear attenuation coefficient, a number, a quantitative number that represent for their ability to attenuate the beam. And I will explain this, what is what the meaning of this number. So for example, the water, it has 0.18 right here, 0.18 centimeter inverse. It means every single centimeter that the X-ray beam passing through the water, it loses 18% of photon. Well, simple, right? So the higher linear attenuation coefficient represents for the higher ability to attenuate the X-ray beam. For example, a dense ball, it has 0.46 centimeter inverse, higher than the air, absolutely almost 0 centimeter inverse. Because yeah, it's also proof that our ball is more dense or have the ability to attenuate X-ray than the air. Just like that, simple, right? And let's go to part 5, section 5, house field units. This is cool too because, yeah, you can see the definition of house field units right here. The house field units quantify the attenuating degree of X-ray beam, just like the beam attenuation right here, coefficient right here. So you may have the question that why we have beam linear attenuation coefficient already, and then why we need another unit, a house field unit. So the reason why behind that you can understand in this way. The house field unit is termed by Mr. Godfrey Housefield, which has a goal to standardize the linear attenuation coefficient. Yeah, it's a standardized unit. And you can see the formula right here. So the house field unit of the water is labeled to 0. And with a material that denser than the water, its house field unit is larger than 0 and vice versa. And the difference between the house field units and the linear attenuation coefficient is the house field unit has the negative number, the negative outcome, my friend. For example, is air. The air is labeled as minus 1000 house field unit. Meanwhile, the bone have 1000 linear house field units. So I think just remember simple. The house field unit is the way we standardize the linear attenuation coefficient to make every process simpler, simple in displaying, simple in processing, simple in calculating. Yeah, just a standardized unit. So we go into the polychromatic X-ray beam. Why? Jesus. It's part 6, I'm sorry. Polychromatic X-ray beam is also one of the fundamental definition that you need to remember. And this line maybe, this section maybe make you confused, but we take it slow, okay? So the first one I want you to remember is the photons from X-ray beam have various energy levels. Well, and this phenomena is called polychromatic X-ray beam. A different word is opposite word, the monochromatic X-ray beam, which has only single energy level in the beam. So let me explain it. Every person always want the X-ray beam that has only one single energy level, but in reality we don't have that phenomena, we don't have that effect, and the photon from the X-ray beam have several energy level, and they call it in the spectrum. Well, you can see right here, you see the picture of the X-ray or CT X-ray beam spectrum, and in reality, in the right side of the graph is a real spectrum in real spectrum shape in reality. So let me explain you more detail. Well, the X-ray spectrum is originated from three kinds of phenomena. First of all, it's a breaking radiation or Bremsstrahlung X-ray. The second one is the characteristic X-ray, and the last one is the filtration activity. So the Bremsstrahlung X-ray is the phenomena occurs when the X-ray, the photon, the electron meets the anode material and it decreases its velocity. So velocity means energy. So the process of decreasing velocity release the energy, release the photon. So that's the X-ray beam. X-ray beam, that kind of X-ray beam is called Bremsstrahlung X-ray beam. So we have the Bremsstrahlung X-ray spectrum here. It's a linear with a number of photons is higher number of photons is correlate with a lower energy. So line is shape. But there's another phenomena occurs when the X-ray meets the anode, when the electron meets the anode of the X-ray tube. Is the characteristic X-ray. This phenomenon occurs when the electron from the cathode goes with a very fast speed, very high speed. So it kicks the electron from the material of the anode out of the atom. So it leads to the higher energy level electron of this material of this atom need to go into the lower level to level because of the, I can say it because of the quantum theory. Yeah, you have a there. Let me show you in words. Insert. So it's too easy. Electron from cathode with high energy, high speed, and they meet kick the low energy electron in anode material. So this leads to the high energy level, electron in that material, remember, in that material need to go into the low level position, low level energy position. So this leads to release the energy, or mean X-ray beam. And a kind of X-ray beam is called characteristic X-ray beam. Well, it's a complex process that but I think we need to another day to talk into details about this problem. But just keep in mind as original of the characteristic X-ray, and the last one is filtration. Filtration is a kind of process we use filter to eliminate the low-level X-ray, low-level photons X-ray, because the scientists believe that the too low energy of the photons doesn't bring any clinical benefits for us, and also it increases the dose for the patient. So we need to filter it out. So usually they use aluminium to create the filter, and you can see right here from the shape of linear the Bremsstrahlung X-ray spectrum, we have this shape after we take into account every single phenomena occur when the electron meet the anode. Yeah, you can see right here the characteristic X-ray beam makes this shape have a peak. Yeah, and the filtration eliminate eliminate the low energy side. Yeah, right here you can see it. Eliminate the low energy side of the X-ray spectrum. So altogether, just remember our X-ray beam have various energy level, and that's called polychromatic X-ray. And the other knowledge, I just want to talk about it for you to let you know that we have everything have the reason why it come into this, why it come to the result. Yeah, just remember this is the most important thing. I will call it direct. So this is core 2 and the polychromatic X-ray beam. Sometimes usually result in the beam hardening effect. Let me explain why. Because the low energy photon can be absorbed by the patient, but the higher energy photon can pass through our body. So while whenever the beam go through our body, is the remaining beam photons is usually the higher energy level photons. So that effect, that phenomena, we call it the beam hardening effect. Let me explain more detail because we have two kind of beam. First of all, it's a soft beam, which includes low energy level X-ray photons, and we have The second kind of beam is hard beam, which comprise of high. I'm sorry, the picture. Okay. Oh man. Oh Jesus. I will bring it into here. Okay. The hard beam is a beam comprised of high energy level of X-ray photon. So whenever the X-ray going through our body, the low energy X-ray photon is absorbed, and is the remaining photons in the high energy level X-ray photons. So that's the reason why this process is called beam hardening. It means you make the beam have more high energy photons, just like that, beam hardening effect. But the beam hardening effect, I think you can see that it's a nature. Okay, I can some notes. Nature. It's a nature phenomena. It's a nature. It's a nature. It's a nature. But whenever this phenomena is so extreme, I mean, your quality of the beam is so poor, right? Your beam is have so large range of spectrum, and the beam hardening effect it occurs so extreme, and absolutely whenever that it leads to the beam hardening artifacts right here. And the reason behind the beam hardening artifact I note here because of the inconsistency beam profile between different types of body part. Yeah, and there are two kinds of beam hardening artifact. The first one is a strict artifact. I think it's a very familiar with the radiologists because they say it all the time. It occurs when our beam meets the dense structure or materials that made by metal, just like a metal implant. So you can see it represents for the dark bands on the images. You see the images of the skull, and this portion right here is the most dense of the skull, densest. So dark bands. The second type of the beam hardening artifact is a cupping artifact, and it results in the vague area on the image because you can see um, it can explain in the way right here. On the body, a middle portion of the body usually thicker than the peripheral portion. So in the slides, so that's the reason why when the X-ray beam going through our body, there is so less X-ray photon come out in the middle portion of our body. So that's the reason why. That's the reason why, my friend. Reason why this cupping artifact exists. It makes our middle portion body in the slides seems like denser, right? Because it's because less photon coming out, and indirectly make the doctor read the image that the peripheral areas is thicker. It is thinner. I'm sorry, it's thinner. What? You can say that. And maybe if you want to discuss more detail about these artifacts, I promise I will have a lecture about all the artifacts appears in CT images. Yeah, and it's an advanced lecture after we gathering all the knowledge about the CT, about I mean the basic knowledge about the CT first, and after that we go into the artifact, go into the how detector works, the detector configuration. Altogether, there's so many things we need to learn. There's so many things that we need to talk about. There's so many dates that we need to meet again. Well, but that's okay for today. That's the end. The end for the part 2 of our lecture 1, basic principle of CT. Well, it's going about to the weekend, and I hope you have a good time again with your families, your children, your parents, your grandmother, grandfather, etc. Well, thank for the patience. until the last words. Thank you and good night, my friend. Bye bye.